Hello and welcome to this episode about recapping. This is going to be an ultimate guide on recapping so you can have one comprehensive reference to do this nice procedure. And follow along with this tutorial and refer back to the Thundertronics blog for the writing up of this tutorial and links to the tools that we're gonna use. But first, what is recapping? I'm sure you heard about that in YouTube and other places like forums, but recapping is basically we desolder all the capacitors that are old in the board and replace them with the new capacitors in their place using the same values. The procedure goes like this. We have this stupid old capacitor, we desolder the capacitor, we do a cleanup on the footprint of the capacitor to make it clean and clean all of that junk that's gonna leak from the old capacitor, and after that we install our new capacitor. But should we recap? I mean, it's a gimmicky word these days, everybody doing this, recap that. Well, there are some faulty capacitors or capacitors that are going to be faulty in the near future, and when they get faulty and when they degrade too much, they will start to leak the electrolyte that's inside of them, which is this stupid and very destructive liquid that you see right here. And as you can see, when it leaks on the board, it starts to damage the board, and we don't want that to happen, especially on tight places where there are a lot of small tracks. These tracks can get destroyed. Like these pictures, the corrosion caused by the electrolyte, the liquid from the inside of the capacitor leaks, can destroy the board. But even in these pictures, I mean, the scene itself is nasty, but the board, I'm sure the board will still work. But for how long? I mean, look at this picture right here. It can be as severe as that the corrosion actually ate up an entire piece of metal, of copper, under the capacitor, plus the traces that's going out of it. And if it left unchecked for even longer than that, it will cause more and more damage. But first, we need to know which capacitors are to be blamed. I mean, we have many types of capacitors, but mainly you are gonna be seeing or facing these four types, which are the ceramic capacitor, the electrolytic capacitor, and what's called the polymer capacitor and the tantalum capacitor. Now we can go all an hour or more even on the types of capacitor, their features, but you should know that your target is going to be mainly the electrolytic capacitor. The ceramics, the polymers, the tantalums are using solid materials inside of them, meaning there are no liquids to leak and to go faulty by that behavior. But the electrolytic capacitor, it uses a liquid electrolyte inside, which can build up the pressure after time with heat and so on, and it starts to leak. But even all capacitors in a board may not be all faulty. I mean, we already identified electrolytic capacitors to be the target, but should we replace all of them? Well, what are the reasons? I mean, what are the symptoms of a capacitor that we know this capacitor is surely bad capacitor? Well, first we have this effect which is called bulging. As you can see, these capacitors labeled as bad, they form some kind of a dome on their roof, and this one, which is the good capacitor, is totally flat. Now this is the first symptom. The other symptom is basically leaking, like these capacitors in this picture. And of course the seal, which is this valve and this seal, is already open, and the electrolyte is leaking and it's getting the damage started on the capacitor, and probably it's going to be leak from the underside as well. So if you see capacitors looking like this, bulging, weird shapes, be sure that they are absolutely faulty. But that doesn't mean that this good capacitor is actually good, because maybe it's leaking from underside. Because look at this, these two are next to each other. So if this one goes bad, you're gonna be pretty sure that this is also bad as well. So the key point to take from this episode and this discussion is that you should replace electrolytic capacitors when you are seeing a problem and with age. Age is the #1 enemy for electrolytic capacitors, and they will go bad after maybe 10, 20, 30 years or so, depending on their quality and rating and circumstances of their operation. So age, for me, for my opinion, age is number one reason why you should replace capacitors. And when you are doing a recap on a board, recap the entire board. Do not go by just identifying one or two capacitors that look bad and leave the ones that look good. But after we want to replace all the capacitors, we should bring new capacitors in. And this is a long discussion about what types of capacitor and what Panasonics or Rubicons or Nichicons, what are these names? Well, the capacitor brands in themselves are really a topic of discussion, and some people really believe in certain brands and disbelieve in certain brands. But basically, I personally identified them to be only two types or two tiers, let's call it that. The best and the good. The best are the Japanese manufacturers, namely Nichicon, Rubicon, Nippon Chemicon, and Panasonic. After that, there comes the Europeans and American brands like Kemet, Ilna, TDK, Worth, whatever. Basically, all of those can be classified as best. And for me, I personally advise going with these four Japanese brands. But there are also the good tier, which is the Taiwanese and the Koreans. The Taiwanese brands like Lilon and Korean brands like Samyang, because these two are being seen used in high-end gear. Like I've seen a Samyang electrolytic caps being used in an Apple charger, which is expensive, as well as the Lilons. So you cannot go wrong with going with any one of those. But since you are doing a recap of your old device, I'm sure that you can go the extra mile or bringing these capacitors that are classified as best, according to me, of course. Now, when you go to buy something for recapping a lot of stuff, maybe you can go to the good tier because it's more economically viable. But in all decisions that you are taking, do not go for any no-name brand or Chinese or something like those. Those are straight out garbage. And this golden tip right here, buy from trusted suppliers like DigiKey and Mouser. Never buy from eBay or AliExpress. I cannot state this anymore because eBay, AliExpress or whatever, these people are basically just getting a shell like this, like Rubicon label, and paste them on Chinese stuff and telling you, hey, it's a Rubicon, because it's not, So don't buy from there, buy from reputable suppliers that you know and ensure that they have the goods that you need. And now you know which brands will you target. But not all capacitors are equal. I mean, what can we buy to replace our capacitors? Well, you look for the capacitor that you already took off and go search for specifications similar to that. Now, what type of specifications does a capacitor have? First, it has the capacitance value, rated voltage, rated temperature and lifetime, as well as equivalent series resistance, equivalent series inductance, is it a polarized capacitor or not, etc. There are many. But for recapping, the most important things are the capacitance value and rated voltage. Always get the exact same capacitance value. Okay, but for rated voltage, you buy the rated voltage of your capacitor or even more. So if you took a capacitor of the board, which is 6.3 volts, you are very safely can replace it with either 6.3 volts or above, maybe 25 volts. Because the more the voltage of the capacitor, usually the more robust the capacitor is, the more tolerant it is. So you can't go wrong with more. Now, rated temperature and lifetime are connected together, but first let's speak about the ESR and ESL. The equivalent series resistance, the lower the better in most cases, because it will heat less, because there are less resistance, and it will produce a purer signal. But these mainly are for designers. But when you replace the capacitors, you can basically go with any capacitor that fits our criteria. And a polarized capacitor, because electrolytics are polarized. This label right here, the gray one, telling you that this is the negative lead, which is shorter, and this is the positive lead. And you need to put the new capacitor in the exact same way the old capacitor was. But for rated temperature and lifetime, this is extremely important for recapping. Let's go for this particular capacitor, for example. I dug that up, and it is a Rubicon. Its capacitance value is 1000 microfarads as seen in here. The voltage rating is 63 volts, which is very high. And it is basically what's called a YXF series of capacitors, which are specifically for Rubicon. Now, when you go to the datasheet, well, unlike women, datasheet actually tells you what's going on. So you go to the datasheet and you check for this label right here. It tells you 105 degrees long life, and it is from 4,000 to 10,000 hours, 105 degrees. Now, what does that even mean? It means if you run this capacitor at 105 degrees continuously, it will run for 10,000 hours basically, because I dug this part number in the datasheet. It is one of those who can run for 10,000 hours. That is what's called the lifetime. Now, there are other ratings like 85 degrees, 125 degrees, and varying hours like 20,000, 5,000, 2,000. Basically, the more the better. If you have 105 degrees, 10,000, that's nice. That's already too much long life, as it says. But if it has 125 degrees, 10,000 hours, it will be a lot better, and so on. Why? Because this will tolerate more and more heat, which means it's more robust. Now, you cannot basically run it for 105 degrees. You're gonna run it for like 30 degrees or so, 25 degrees room temperature. Maybe it's next to a hot source. It will maybe 40 degrees. That will go by this 105. You can basically estimate that the number of hours that this can run. So if we run it at 52.5, which is the half of that, it can run for 20,000 hours. Now, all of that is calculated. Now, the problem with capacitors when they derate over time is that their ESR changes. So now if this ran on very bad conditions and you took too long to replace it, now maybe even the capacitance will change. Now it will not be 1000, maybe it starts being like 900 or 1200. It can change. And of course the resistance, internal resistance, the ESR can change. Sometimes getting to 20 ohms, 30 ohms, which basically makes it absolutely useless for pretty much anything. So age is number one factor you need to take into your account to replace capacitors. Don't just look at them and say, hey, this one is a flat top, it's clean, yeah, it means nice. Yeah, it's 30 years old, but it's still nice. No. After 30 years old, pretty much you're sure that these capacitors have degraded over time. And it is a nice practice, like paying $10-15 for a capacitor kits to save your precious device and make it run flawlessly for the next 20-30 years. That's a steal. That's what I'm telling you. Maintenance is always recommended. But these capacitors, the electrolytics and the polymers, for example, they come in basically two forms, either through hole or surface mount, just like any other electronics. But the surface mount, as you can see, it can come with this radial shape, the traditional one, and in many odds and shapes. Of course, whatever you can get to replace them, that's gonna be on you, but generally you're gonna find exactly the same footprint. For through-hole capacitors, there is also this type, which is the axial capacitor, which is the leads coming from the sides, not from underneath. So basically, it's nice to know which capacitors are you facing. Maybe if you see like something like this, some dumb people might think it is a battery or something. No, it's a capacitor. And you need to look it up and you need to replace it with exactly the same version. But replacing capacitors will tend to be a very easy task, but at the same time, many people have done it wrongly. I'm gonna list here the number of errors or mistakes, in my opinion, that I think and I see other people are doing. Number one has to be the non-flush installation, like these pictures right here. Look at this. This distance from here to here is wrong. This one, of course, not only that he gets it like the wrong capacitor, because this from here to here, this distance between the two leads, it's called the pitch. So you need to match the pitch between the capacitor legs and the pitch between the board itself. This one is, I suspect it is 3.5 millimeters, but the board is 5 millimeters. So getting the correct capacitor not only relies on what I've talked about in the previous slide, but also on getting the same pitch and the same dimensions. We can result into something like this, and now we can solder it, and it will first of all increase the ESL and ESR. Now this lead, see this is extra inductance and extra resistance. May or may not affect your operation, but this is objectively wrong, and you can basically avoid that by cleaning up the joints and push the capacitor down and solder it properly to be totally flush to the board. This weight, look at this, puts the weight on the leads and solder joints. Imagine if this capacitor is actually a lot bigger than this and the joints are small. Now the solder over time might crack, and it may be physically collide with other things like a shell or something above it. You recapped it and now it doesn't fit anymore, and you need to twist and do stuff like that. So you can result into something like this. Look at this. When bent, can strain the leads. The leads seal. This is the leads and the seal is inside. Now when you like bend it so closely to the leads like this, you're gonna put some pressure on here, which will accelerate the degradation of the seal and will make it degrade faster and will leak faster. So overall, do not by any means do something like this. Okay, do it properly, do it like an elitist, if we are gonna call it like that, and you're gonna be the best recapper ever. Number 2, which is something I really hate to see, which is a through-hole capacitor on surface mount footprint. Like, why? Look at this. This is a surface mount capacitor, and this is surface mount capacitor next to it. Now, why do you replace it with an electrolytics and do something like this? Aside from ESL and ESR increase due to the long leads, you're gonna have like maybe a centimeter or 2 sometimes, or even more of leads. It can leak on multiple places. If anything wrong went with this capacitor, not only will it leak on the footprint underneath it like any other capacitor, but look, it can leak on here. If this gets hot, this chip can get hot as well, and this can leak over the chip and you may lose it. Replacing a capacitor is one thing, replacing an obsolete chip on an important device, that's another thing. And of course, it can strain both the leads, the lead seal, the solder joint. All of that will be stressed. It will not be like this capacitor sitting properly and nicely. And most importantly, it's not professional. Like, you can buy any capacitor that you want these days. You're not bound to some shop. You can go and pick the correct capacitor, surface mount for surface mount, through hole for through hole, exactly as I said in the previous slides. So please don't do this. Another thing that I see very often, unfortunately, is a ceramic capacitor instead of an electrolytic one. Now this topic is with an asterisk because this can work and sometimes should be done. But there is something about ceramic capacitors is called DC bias, which is that this ceramic capacitor actually changes its capacitance value with respect to the applied voltage. It means like this. I have maybe a 10 microfarad electrolytic capacitor hooked up to 12 volts rail. Maybe this is 12 volts to the electrolytic capacitor. Perfectly fine. I want to replace it. As you can see, this has started to leak. This is still not the one who soldered it did it without cleaning, which is a mistake. And if I solder the 10 microfarad capacitor, ceramic capacitor, totally fine, spec'd very well, perfectly fine, I put it right here. But the data sheet, because unlike women, data sheet actually tells you everything exactly the way they are, this capacitor might even be mere 1 microfarad at 12 volts, because it is 10 microfarads ceramic capacitor only at 0 or 1 volts maybe, and the curve degrades by after that. At 5 volts, maybe it is like 6 microfarads. At 12 volts, maybe 1 microfarad. So the circuit is expecting 10 microfarads to work properly, but now you only give it 1. That surely can cause problems. But if you are extremely sure that this ceramic capacitor at this voltage with its degradation can work perfectly fine and the circuit has no problem with that, especially with the low ESR of this capacitor compared to the electrolytic, you should go for it, because ceramic capacitor is just better than the electrolytic capacitors. Here's the tip. Only do this when you are 100% sure and tested that it works, because of the DC bias and the low ESR, stuff like that, but mainly the DC bias. Generally, it is not recommended. So I do not recommend doing that, especially that there is another better solution coming up, which is the polymer capacitor. Now, polymers are generally superior to electrolytics, but replacing old electrolytics with polymers sometimes cannot be done due to their very low ESR. So instead of just of the DC bias and the low ESR, now only we should care about the low ESR, because the polymers do not have any the DC bias. Here's a quick comparison between electrolytics and polymers. The electrolyte used is a solid polymer instead of liquid, which is the best thing, because this thing shouldn't be replaced, because it does not need replacement. It will not go bad like electrolytics. ESR is significantly lower, meaning if you have a filtration network for your power supply, the electrolytic capacitor can heat too much because it has high ESR, which has a lot of voltage drop on it, which will heat. But the polymer capacitor is basically non-existent, because it's extremely low ESR and it will never heat like the electrolytic capacitor, if any. So this is hands down one of the best features ever. And your power supply, as we see from this rating, the ripple current handling will be better, because this can tolerate a lot of ripple current in your power supply, a lot of noise. All of that will be absorbed and tamed perfectly well by the polymer capacitor due to the low ESR that it has. The lifespan is significantly longer. Some people say that it is 5 times to even 10 times the electrolytic capacitor, because, as I said, there is no liquid to degrade and to evaporate and stuff like that. Now, all of this is, of course, assuming the proper usage. I mean, if you put the polymer capacitor next to a torch, it will eventually go bad. But we're talking about sane people using sane devices. The voltage rating is one of the electrolytic capacitor advantages over polymers, because till this video I don't see polymer capacitors being rated for extremely higher voltages like 200, 300, 400 volts. But electrolytics can basically has that no problem. And high frequency performance, the polymer of course is better, as we talked about in the previous points, because it has low ESR and stuff like that. And this can be a good feature to have the polymers instead of the electrolytics, in case you replaced your old power supply, which can be linear power supply, with a modern switching power supply, or a old switching power supply with a new modern switching power supply which uses higher frequency switching like 1 or 2 megahertz, which will introduce high frequency ripple and high frequency noise, something your old device was not meant to have. And the electrolytics capacitors will not filter that as good as the polymer capacitor. So maybe having a polymer is an upgrade. But the electrolytics still cost significantly lower. Now, due to the low ESR, what other problems can happen? I mean, older circuits, as I said, was not really designed for high frequency switching or high frequency stuff. Therefore, their control circuitry is very slow, and it relies on finding some form of ESR in their path. So that if it doesn't find this ESR, because we have put polymer capacitors, now it has low ESR, basically nothing, it will think that there is a short circuit in your device, on your circuit, and it will malfunction. And if you have amplifiers or even power supplies, they may oscillate because their control loop was not really meant to go with low ESR. Now, of course, you can put some damping and stuff like that, but these are only for very, very advanced people. So how can you know that your old device can tolerate low ESR or can't? Well, my answer is testing, because testing is the only thing that you can do to verify. For example, for retro gaming community, I think that people should just put a table or a page or a wiki for devices, and people start trying putting polymers in these devices and report back. So that's how the community is building this knowledge base that about each device, whether it can tolerate polymer capacitors, low ESR or not. This can be very beneficial, because if you are sure that your precious device can tolerate polymers, then you should use polymers instead of electrolytics, because they are significantly superior. So testing is the only thing that is good. Now there is an asterisk right here, right here. Instead of the solid polymer for the electrolyte, there is also the hybrid polymer capacitor, which has both solid polymer and electrolyte liquid. Now this hybrid is not really recommended, because you're gonna reintroduce a liquid electrolyte again if you are replacing it. It also has ESR similar to polymers, but people say that it has more reliability than polymers. I don't necessarily agree. It has more stable capacitance over temperature than the electrolytics, and it has basically better current leakage performance than the polymers, which means this thing is the best of both worlds at a price and at the right place. The automotive industry somehow likes these types of polymers, but for me, do not go this route. It's useless, and it may be a bad thing in the future because of the introducing of the liquid electrolyte again. So either electrolytic capacitors, regular ones, or polymers when you are very sure. Speaking of the tools, we need to dig into desoldering tools. These are the three tools that you are going to be faced with: the hot air station, the soldering gun, and the hot tweezers. Now, the hot tweezers are more of a specialized tool, which is basically useless for anything else. This is gonna be the least destructive method, because the hot tweezer, as we can see in the video next, can desolder the capacitor basically harmless to the board. The absolute must is these desoldering guns or stations. Buy this Heiko brand or something Chinese but good quality, and if you're really into desoldering a lot of stuff, basically invest in this Heiko one or something similar of high quality with adjustable tips. This can suck the solder from through hole joints better than any other manual plunger type or bulb type stuff. These are just basically useless. And the hot air, of course, if you can afford or have space for a hot air, it's always a nice decision, because it's also one of the methods that you can use to harmlessly desolder the capacitor. Soldering tools are you gonna need it, because you're gonna solder the capacitor or maybe desolder the capacitor, as you will see. Get a solder which is a nice quality, and get a thinner one, not like this picture. The thinner the better. And the soldering, get a soldering station. The unit is one side, the iron on the other side. Do not get one of those which is just the iron and it plugs on the wall, no adjustability. No, I recommend going with the Heiko brand. Get yourself a really nice Heiko FX888D. This is very standard, hobbyist or professionals. $90, maybe $80, something like this. Absolute bargain. Other tools that you're gonna need: solder wick for basically cleaning up the pad or the joint, as we explained in the first slide. No clean flux, highly recommended to make your board safer to operate, to prevent like mistakes and stuff like that, and to make it a lot easier. Tweezers, side cutters, pliers, whatever you can get your hands on, and of course the 99% alcohol for cleaning the pads after you wick it with the solder wick. Miscellaneous stuff like Q-tips, Kapton tapes, helping hands, brushes to clean stuff, pliers, basically whatever. Now for desoldering the surface mount components, we have several methods that we use. The first method is as seen in this video. It's called the rocker or swinging method. Basically use the soldering iron with the tweezer, heat the two pads of the capacitor one at a time and rock it sideways like you see in this video. Now if you do it correctly and carefully, this can be a non-destructive method, and basically the capacitor after that will be desoldered safely without compromising anything. Next is the twisting method, which is done by a plier like this, and you hook the plier to the capacitor, start gently swinging left and right, twisting left and right until you feel that the capacitor just let go of the board, and you can basically just get it up like that. Now the capacitor might leave these plastic pieces. You need basically to clean up, and it can leave something like this leftover legs of the capacitor, which you're gonna clean using the solder wick and the soldering iron, and basically continue from there. This is one of the most destructive methods, but I find that if you are very gentle and very careful, rarely you can cause a problem, because as you can see, the pad is still connected to the leg, and when you hook it up quickly before it lets go, you can basically tear off the pad. Next method is one of my best favorites, which is the snipping method. Basically, touch the capacitor with a tweezer and push down, then with the side cutter, gently cut it up until it gives up like this. And be sure to gently cut off the rest. Do not yank the capacitor up before you feel the snips, or else you will take with you the pad or something on the board that you don't want to take, like traces and stuff like that. I recommend the snipping method over the twisting method generally, because it is less destructive. And finally, the hot air, self-explanatory. As you can see, this is very non-destructive method, basically heating it up until it goes up like that, and clean up afterwards. You can use Kapton tapes, for example, to cover around the capacitors to prevent heat from damaging other places, because this is direct heat we're talking about. But this is a time-consuming method, and maybe you don't have enough time for that, but if you do, this is a recommended one. The last one is called the hot tweezers. As you can see, the tweezers like a double soldering iron. It hooks up to the pads, heating them gently, and you basically take the capacitor off. This can be destructive if you touch the capacitor instead of the pads, but generally you want to touch the pads until they give up. As of course, you know that the through-hole desoldering is using the desoldering gun, as I'm doing in this video. Heat up the joint and basically suck it up until the capacitor has no solder on its leg, and you can basically take it out like this. This is why the desoldering gun is a must for through-hole operation. Now, this tutorial or ultimate guide has ended. Please visit thundertronics.net and the blog and Thundertronics store. And the next steps for me and for this series is gonna be a playlist where I completely desolder and solder new capacitors for my retro gaming devices, such as PlayStation, Nintendo 64, Super Nintendo, whatever. And there's gonna be a dedicated video for each device. So please like and share the video, subscribe to the channel and share these playlists and videos for your colleagues, and please follow along with other tutorials I'm gonna make in this channel. So stay tuned, and I'll see you next time.